Welcome to EDU World Space.
The goal here is to determine the time between two successive oppositions of Mars. Oppositions are ideal times to observe Mars because it is opposite the sun in our sky. And what is involved in doing the prediction is to understand the difference between a synodic period and a sidereal period. So the formulas that are given involve 1 over s, which is the synodic period, which we'll discuss. The sidereal period shows up in the formula as a p. And the difference between those is sidereal means against the backdrop of stars with reference to these stars. So think about the Earth going around the sun. Makes a nice orbit, and every year we come back to the same alignment against the backdrop of stars. So, for example, you can come back to the same sign of the zodiac in your sky, and you know you have gone through 1 year. If that zodiac sign is showing up at the same time, at the same altitude in your sky. So this is one sidereal period. For the Earth, this is 1 year. And the little symbol up there with the plus in it means Earth. Synodic, on the other hand, usually refers to an alignment between the Earth and some other object that is moving around the sun. So these alignments, of course, are very important in terms of astrology. So people wanted to know how to predict them. So we'll show the one here, the particular alignment. It's not the only alignment, but it's the particular alignment that we're going to talk about. And it's where the planet Mars is directly in a line between the Earth, not between the Earth, but past the Earth, in a line with the sun. So everything's all lined up. And that can happen in any place in the orbit. I mean, it could happen where I've drawn it. It's the simplest way to draw it. But it could also happen almost anywhere. So one of the things people noticed is that there wasn't always a constant time between the alignments. And this is how the non-uniform motion of the planets became a sticking point, is that Mars did not always line itself up in a exactly predictable way, and you needed some tricks to put in predictions that are better. The formulas up above are predictions of the synodic period when Mars returns to the same alignment after having been in one with the Earth. Mars is an exterior planet. That's what the word interior would mean inside Earth's orbit. So we're talking Venus and Mercury, whereas exterior is everything else that orbits outside the Earth's orbit around the sun. But we can predict the synodic period, but recognize that these equations are based on uniform circular orbits. And we'll see that they do a pretty good job, but they aren't perfect, which is noticeable within days off, if in some cases even weeks off. So let's calculate the time between oppositions for Mars. What do we expect? Expected delta T between two oppositions of Mars. And of course, we know what the period of the Earth is. It's just 1 year. By the way, those formulas come about because we are on a moving platform and we're observing things that are moving relative to us. But anyway, the period of Mars is 1.8812 years. We'll be kind of precise here. And working that out, 1 over the synodic period is 1 over 1 minus 1 over 1.8812. And working that out, the synodic period turns out to be 2.1 years. Okay, so that is true if there is uniform circular motion. But we now know, of course, that planets orbit in ellipses. And so we would like to model the elliptical orbits a little bit more precisely in time. I did not actually use the orbit equation, although I checked my work, but I actually made an Excel spreadsheet. And the first thing that I had to do, of course, was figure out the data for both the Earth and for Mars. And so we have to input the sidereal periods for each in years, the semi-major axes in astronomical units, and you can use Kepler's third law for that, p squared equals a cubed, and the eccentricities of the orbit. And even Earth is a little bit eccentric. Not a whole lot, but it is a little bit. Mars is practically the planet with the largest eccentricity in our solar system. And I won't get into the details of modeling the time dependence, but I did use Kepler's second law to model time dependence. And I also use the orbit formula, the conic section. R is equal to A times 1 minus epsilon squared over 1 plus epsilon cosine of theta. And basically looked at a lot of data, but the first experiment that I needed to figure out how to do was to get the Earth to be at aphelion at 0 degrees. So here's Earth. And simultaneously have Mars at its perihelion at 0 degrees. And the formula for the conic section, just to note, has basically when theta equals 0 degrees, it's our perihelion. So for the guy you want to shift to aphelion, you have to revise that formula. And basically just rotate the ellipse by pi. Okay, so flip it around. So the first formula has our perihelion at theta equals 0, and the second one has our aphelion at theta equals 0. And basically printed out XY coordinates and R values for both Earth and Mars as functions of time, and then looked through the data for when they were in alignment again. That was not easy. So see when Earth and Mars return to initial alignment. And for me, it was always making their angle difference, theta difference, equal to 0, since they both started out at opposition with theta, a difference of 0 degrees. And what I found was the following, is that this first experiment, we'll call this experiment 1. What I found is that at t equals 0, they were, of course, at opposition, and the difference in the distances from the sun was 0.3637 astronomical units. And then, let's see, at t equals roughly 2.205 years, I didn't do lots and lots of data points. They came back to in alignment, but the delta R was bigger. So the first thing to note is that because you start off with a close encounter, the closest possible, the next one going around is going to be a little bit different. So notice that I predicted, though, or from the model, the time in between oppositions is longer than the prediction of 2.1 years. There it is. Yeah. There's the prediction. And here is the model. We should not be surprised that those are not exact, because the formula is true only if you have perfect uniform circular motion, which we do not have. The second experiment that I ran, number 2, is kind of the obverse. I started again, but I flipped around the Earth was close to the sun, and Mars is at aphelion. So I rotated the Mars orbit by pi, according to the equation. And then what I measured was at t equals 0, they were separated by 0.684 astronomical units. And then 2.09 years later, they came back together again in alignment, and the delta R had gotten smaller. So again, we see that the separation between the two changes from opposition to opposition. Again, evidence that these are not circular orbits. And the time varies. Neither one was precisely with the calculation, although they were close. But again, this is what is to be expected with non-uniform elliptical motion under gravity. So yeah, very interesting. The other thing that's interesting to note is there's quite a variation in the difference in radii, and that is what you can see will result in a different brightness. Because we're closer to Mars, at some times during opposition, Mars will appear brighter, and noticeably so. And of course, those are the so-called favorable oppositions, and people get really excited about going out to view Mars during those particular oppositions.